All right, welcome back. Getting into the next section of our logic and reason unit here. Last time we just kind of introduced proofs and working through the idea of can I condense this so that I have my statements on one side, my steps, and then my reasons, my why for doing all that on the other side. So we're practicing that more today, getting into more of the meat and potatoes of proofs that we're doing. Specifically, we're doing that with line segments. So we tried to practice with algebra a little bit, and we'll throw in some more algebra today to make sure that we're comfortable with that. And then we're also throwing in some ideas that we've already talked about in geometry and trying to build on those to be able to create proofs, okay? So section for today is going to be 2.4, segment proofs. As always, make sure you're keeping these notes in order. Date today is the 8th, and then objective is you want to be able to set up and complete 2-column proofs involving anything involving line segments, okay? So like I said, using some geometry ideas now that we have started to practice proofs a little bit. So few things here. We talked about this a little bit last class where we have these theorems and we have these definitions that we want to make sure we utilize. Okay, so we're going to talk through a few things that we've already talked about and kind of review, and then some new theorems. So first one here, midpoint theorem. We have discussed this before, but now we need a specific geometry theorem or definition for it. So midpoint theorem says this. I'll get this here. It says if M is the midpoint, and of course M could be any letter, doesn't really matter, but if M is the midpoint of line segment AB, then what this means for us is it means AM is going to be congruent to MB. Okay, AM is going to be congruent to MB. And if I want an example of this, obviously we can kind of draw this out if we like. Line segment AB. Okay, and then M. And then like we said, since AM is congruent to MB, we mark that on our diagram with a dash mark on each of those lines that are congruent. Okay, so like I said, we've talked about this before and we've solved problems with this, and now we're getting more in depth in not only saying, can I solve this, for a variable, but would I be able to prove this to someone else who only knows, geometry terms and nothing else, okay? And we'll talk about what that looks like. Second one here, segment bisector. We've talked about this before, just want to make sure we review this just in case we see this on future problems, and this will just be the definition, okay? Segment bisector simply says this. This is just a line or a point, that divides a segment, into two congruent halves. Okay, we'll see that word bisect a lot throughout this year, so make sure you understand what that means. It means it's cutting it into two congruent halves. And we're reviewing this not only because we need to make sure we remember it, but also because we're going to see proofs where I'm given information where it says this line is the bisector of segment AB. And so I need to be able to define that or be able to use that as a reason in my proof, okay? And then last one here, segment addition postulate, another one of these concepts that we've already talked about, but now we're giving it a specific name and want to be able to use this in a proof. So segment addition postulate says this. It says if point, let's go point E, is between, if point E is between point D and F on a segment. Okay, so if I have one line segment here, or one line, and E is between the two, then our equation, or what that can look like, is we know the piece plus the piece is always going to equal the whole thing. So DE plus line EF, or segment EF, is going to equal segment DF here. Okay? Again, using more of geometry wording to show what that equation is going to look like. Then DE plus EF equals EF, or DF, excuse me. If I want an example just to visualize this, just create a segment just like the description says, DF, and then E has to be somewhere between it. Doesn't matter where it's at. Could be dead in the middle, could be to one side or the other. But like we said, we know segment or piece plus piece equals the whole thing. And like I said, we're using this in proofs now, and we want to be able to use this postulate as one of our reasons. And we'll look into some examples with that. Okay, so example 1 here, with all this in mind, I'll give you a second. I want you to sketch this diagram for me. Shouldn't take too long. And then I want you to write all this information down. Okay, so take a sec, write this, or actually, I lied. Okay, don't write this information down because we'll write it in our proof. Okay, so pause your video, draw the segment, then come back. Okay, so hopefully you should have the diagram drawn by now. We always look at that information, and we're saying B is the midpoint of line segment AC. So that's one piece of information we already have. And then we're told AB equals 2x minus 3, and then BC equals 27 minus 4x. And our goal is trying to prove that x equals 5. So it's still kind of like an algebra proof, that we've done before, but now with these kinds of problems, we have to show our setup as well. So hopefully we know how to set it up. Now we actually have to be able to prove that. Okay, so first thing I'm going to do here, anytime we're doing a proof, is I'm always going to have my statements and reasons. And I'll move over here. Okay, statements on the left side, reasons always on the right side here. Okay, so first thing, like we talked about, first reason is always going to be the same in every single proof that you always do. First reason is always going to be given. You're always just taking your given information and you're writing it down. So this is why I said I don't need you to write down what the given is, because we're going to put it in the proof already. Okay, so this I do need you to write with me. We're going to say B is the midpoint, and I can abbreviate that if I need to, midpoint of AC. And we'll talk through these different ways to abbreviate as we go through proofs, because it is much more writing than you're used to in math class. Okay, line segment AB equals 2x minus 3. And then line segment BC equals 27 minus 4x. Okay, again, not even using much brain power there, just rewriting what happens. Okay, and one thing that I will mention in this as well, because I had a student try to do this last year, where I gave him a test and he said in the given information he didn't write anything down, he just circled it and then drew an arrow to that box. Okay, don't ever do that. I did count him off points for that. That's just being lazy. You need to make sure you're always writing down all of that given information. Okay, so with this being said, now as we're trying to progress through our proof, this is where a lot of students tend to struggle, is I've got the given down. I obviously can rewrite things, but now where do I go from here? So you're always looking at the given information and you're asking yourself this question: what other information do I know from this? What other statements can I make? That's what you're always doing. Always focus on the given first and see, is there other information that I can gain here? So for instance, if I tell you B is the midpoint of AC, that should automatically tell you more information. Specifically, it's telling us how we are going to set up our equation. So if I go back to that midpoint theorem that we just wrote down, it says, well, if I have a midpoint of something here, if I have a midpoint of something, then I know those two segments, those two smaller segments, are going to be congruent to each other. So that's exactly what I'm going to write. I'm not going to plug anything in yet. I'm not going to have any variables or anything. I'm simply just going to write that the two pieces, or the two smaller segments, are congruent to each other. So if B is the midpoint, if I look at that picture, B is the midpoint of AC, that means I know AB is congruent, and specifically I'm using congruent because it's just like we wrote it in the theorem. AB is congruent to BC. Okay, and the reason for that, like we just talked about, that is the midpoint theorem. Okay, if you would like to abbreviate midpoint, you can. If you'd like to abbreviate theorem, we always abbreviate that as THM. Okay, so we're always setting this up first. Now we have this here, and we have what the actual length of AB is and what the actual length of BC is in terms of x, but I don't have that equal sign in the middle because I don't want to try to do an equation with a congruent symbol here. So my next step before I get started is I'm going to convert that basically from a congruent symbol to an equal symbol. So now I'm going to say for my next step, AB is equal to BC. And it is very important that you do these two steps. Show what the midpoint theorem says, they are congruent, and then we know as geometry students, if we see that word congruent, that just means equal. That just means equal lengths or same lengths. And my reason for that, why I can change it from congruent to equals, is that's just what congruence means. That's just the definition of it. So I'm literally going to write definition of congruence. Okay? And if you run out of room, that's okay. Like I said, we'll talk about different ways to abbreviate these as well. But that is the definition of congruence. I only use that because I see this misused a lot. I only use definition of congruence when I'm going from saying something is congruent to something is equal. Okay? So now I have AB equals BC. Now that I have the equal sign, and now that I have these two segments, I can plug things in because I know what AB is. I know AB is, it tells me, is 2x minus 3. So I'm going to plug that in here. 2x minus 3, and then equals BC. What does that equal? I already know that. That's 27 minus 4x. This is the point that we're trying to get to. We show the setup first, just with the names of them, give our reasons how we know this, and then we can plug things in and do our algebra proofs from there. Okay? And then the reason for this, how do I know that I can go from the names to the actual numbers or in terms of x? Well, I said I plug things in, right? Another word, if you can think of a word that we use for plugging things in math, we call that substitution. Anytime I substitute something in, and we talked about that principle a little bit last time. If I substitute something in, that's when I have two things that are equal to each other. So I just plug in one for the other. Okay, so that's substitution. And then from here we can solve. And there's multiple ways to do this. I'm going to say, let's say we were to add 4x to both sides because I like getting rid of the variables or isolating the variables first. So if I were to add 4x, if you'd like to, you can actually put the plus 4x, but hopefully you're getting skilled enough in algebra to be able to just kind of show what the next step would be. So for instance, once I do that, I'd now have 6x minus 3 equals 27. Okay, so you can write the plus 4x, but you don't have to. Okay, it saves us a little bit of time. And my reason for that, well, I added something to either side of the equation, so that is the addition property. Addition property, and specifically this is the addition property of equality. Okay, and I will write that out. All right, next step here, same kind of thing. I have a negative 3 or a minus 3. I want to add that to both sides, so I'm going to show what that looks like. Again, I can write in the plus 3 if it's not making sense. But we have this here. Again, how did I get to 6x equals 30? Well, I added something to both sides of the equation. So this would be the addition property. Again. And then last step here, because we're almost done, if I gave you this equation, hopefully you would know you divide both sides by 6. And when I do that, I get x equals 5. So that's my final thing, and I see that's what I was trying to prove, so that's good. And then the question is, what's the reason for that? Well, I divided something from both sides, so that is the division property of equality. Okay, so notice we're kind of taking a step up now. We're not just going through the algebra proofs and being able to say, I added something, I divided something, I subtracted, whatever. Now we're trying to show, here's how I can set this equation up, and here's why. And that's going to take some practice. This might not make sense or click right away. Okay, and that's why we're doing these kind of notes, and we'll have assignments to practice this as well as activities. Okay, so let's continue with this. Let's practice a little bit more. Let's go on with this one here. Let's say we're given this. We're not given a diagram, and in fact, I'm going to actually have us draw or sketch a diagram with this just so we can visualize a little bit. But we're told here jk equals 17 plus 2x, kl equals x plus 17, and then JL equals 13. Okay? And then I want to prove by the end of this that KL equals 10. So what I'm going to do to start here is I'm going to try to draw this out. I kind of notice here I have all these different segments, JK, KL, and JL. Okay, so I want to draw a line to kind of show that a little bit. Okay, it looks like the big piece here, K is in both of them. It looks like it's between J and L. So I'll draw K here, J, and L. And sometimes you'll be given a drawing with this. In this case, I'm just drawing it out for us. Okay, and then if I want to, I can label these as well. So we said this is 17 plus 2x, x plus 17, and then JL equals 13, the whole thing. Okay, I want you to sketch that out with me if you haven't already. Okay, and the good news with these proofs, hopefully that we mentioned before, is that they always give you the answer. Okay, I'm not trying to hide what the final answer is. I'm not telling you to find KL. I've already found it. It's 10. I'm telling you that's the answer. Now you need to show me and prove to me how we got there. Okay, so the way we're going to do this, again, bring this over here. Erase that. We'll draw our two columns. We have statements and reasons as always. Okay. We know first reason is always going to be the same. It's our given information. And we're just going to take a second. We're going to write all this in. So we're told JK is 17 plus 2x. KL equals x plus 17. And then JL equals 13. Okay, so if I just gave you this problem normally, I'll give you a sec to write all that down. Okay, if I just gave you this diagram normally or in the past, last chapter, hopefully we understood how to set this up. And we got a lot of practice with it. Piece plus the piece equals the whole thing. We're going to do that same kind of problem here, except before we dive into actually solving it for x, we need to show how we set it up. So I look at my given information, I've got this diagram, and I need to show how that equation is going to be set up. Well, we know piece plus piece equals the whole thing. So in this case, if I look at this, this is going to be JK plus KL equals JL. I'm always using the names first before I plug things in. And my reason for that, well, if we scroll back up to what we wrote down earlier, is we said the segment addition postulate tells us if we have a point in between a segment or in between two other points, then it's always going to be the piece plus the piece equals the whole thing, or in that case, DE plus EF equals DF. And those letters could be anything. So in this case, we have our point in between JK, and then the 2 points that's in between is J and L, so I can say JK plus KL equals JL. My reason for that, like we just said, is going to be the segment addition postulate. Okay, segment addition postulate is what we're kind of relying on for this one. Now that I have to set up, and now that I have an equal sign, I don't need to worry about changing it from a congruent symbol. I can just plug these in. So I know JK equals 17 plus 2x, KL equals x plus 17, and then I know JL is 13. So I can plug all these in here. Same question as before, what's the reason for that? Well, we know we plug something in, so that's just going to be substitution. I'm just taking what something equals and plugging it into that spot. All right, and now that we've got everything plugged in, now we can solve like normal. So a few different ways to do this. I would recommend doing combine like terms first. So when we combine like terms, we have 2x and 1x. That's going to give me 3x. We have a positive 17 and a positive 17. So when I combine those, it's going to give me 34. And then final one here, it just equals 13, right? My reason for that, how do we know we got to that next step? Well, just like I said, we just combined like terms. So I'm going to write that in, combine like terms. Okay, we'll continue here. We'll try to go a little bit quicker. Next step is we know we subtract 34 from both sides. So when I do that, I have 3x equals, and then you could just do 13 minus 34. And that's going to give me negative 21. And it's okay if we see a negative for right now. Okay, reason for that, we subtracted something from both sides, so that's the subtraction property of equality. Okay, and then final step to find x would be to divide both sides by 3. So I divide both sides by 3, and I get x equals negative 7. Okay, and my reason for that, like we said, since it's division, is division property of equality. Okay, moving a little bit faster just so we can try to get through this proof, and hopefully this is just a review of what we did last class. Okay, and then this last step here is actually a little bit new, because notice here it's not asking me to prove that x equals -7, so I'm not done yet. It's similar to what we've done in the past. I need to check and see, do I need to plug this back in? In this case, I do. So we're told that we're trying to prove that KL is 10. So what I need to do is I need to plug this back in here. So I'm going to say KL equals, and then we know earlier we said it was x plus 17. You see that at the top. So I'm plugging back in x now. So -7 plus 17. And I'm going to put the -7 in parentheses just because I'm plugging it back in. Okay, so this adds on a couple extra steps here. But first of all, KL is -7 plus 17. Well, how did we know we could put -7 in there? We just substituted it in. We just plugged it in. So that's substitution again. Okay, and then final thing here. If KL is -7 plus 17, we know that's just 10. Okay, and it's not necessarily a property. It's not, you know, the addition property, the subtraction property, anything like that. It's just simply doing the math, right? -7 plus 17 is 10. So anytime I have a problem like this, and it's usually going to be at the end of these when I'm plugging something back in, if I just simplify the equation, then that's what I'm going to write as my final reason, is I'm just going to say simplify. Okay, don't have to worry about addition or subtraction, because when you plug something back in, it's just understood in math that we always just simplify it. So that's my reason to simplify. And now we are done. We have shown that KL equals 10. Okay, so that is the second proof.